Hi everybody and welcome to a virtual tour through the IoT, Systems and Industrial Security Research Group. I'm Georg, I'm mostly in charge of the show and I will be your guide today. But before we go into the meaty details of our research, let me give you a quick introduction about the group and its activities. So, who are we? This is us, hard at work as always. Currently, we are 10 people in the group, not counting a varying number of students that we are working with on different topics. But what are we doing apart from research? So, for one thing, we're heavily involved in teaching activities. We hold different intermediate and advanced lectures on security at TU Wien, and we have about 250 students participating in our courses per year. Additionally, we help motivated students on the way to the bachelor and master degrees. And for those that still haven't had enough of us, we're furthermore also organizing a CDF team, namely We Own You. While it's also very interesting to dive deeper into topics, it's also mostly fun to solve challenges together. So, this concludes our general introduction of the group. Thank you for listening so far. Now, let me give you a quick overview of the topics that we are working on. As a side note, if you ever see this marker and this label pop up during our tour, it indicates a student project that we have either finished or are currently working on together with a student. So, without further ado, please follow me on our adventure.
Our adventure starts with the Internet of Things. Although IoT has led to a lot of advancements in various sectors, not everything is as good as it might seem. As the saying goes, the S in IoT stands for security. And this is where our research begins. We investigate the security and privacy aspects of the Internet of Things and related technologies. While there are lots of different deployments of IoT, a smart home is nicely suited to show security and privacy problems, but also convenience versus safety critical applications. So now we have all these smart devices, but what is the point of being smart if you can't tell anybody? Therefore the devices need to somehow interact with the outside world. Some of these devices might be talking to each other, others use a hub or your smartphone as a means of communication. And then there might be those that are talking to the cloud. Of course the cloud is not a magic place, just someone else's computer systems where backend services might be deployed in VMs or containers which might have security problems on their own. And while devices might try to communicate securely, apart from vulnerabilities, there is still the human factor that needs to be kept in mind. This is the expertise of Katharina and Alexandra, who just returned from Japan.
Due to different user misconceptions, there are some application problems in the wild, like for instance, poor HTTPS configurations. The reason for this is that administrators are confronted with very complex cryptographic algorithms which are too complicated for them to understand. To investigate the roots of these misconceptions, we conducted a qualitative user study. Therefore, we recruited 30 participants and performed drawing tasks based on 3 different scenarios with each of them.
Our findings reveal severe misconceptions about the security benefits from both groups. End users, on the one hand, for example, confuse encryption and authentication, and also they ignore or distrust the security indicators provided by HTTPS. Administrators, on the other side, do not know what certificates are or how they are used in this protocol.
Additionally to the security of communication, of course the privacy is a concern, as these devices might collect and transmit personal information as well. Another question that arises is the security of the devices themselves, as their exposure makes them a target for attacks. So let's take a closer look at what actually makes such devices smart. When we open our smart bulb, we find among other things a circuit board. On this PCB we can find an MCU, which in turn is controlled by firmware. Since our work mainly deals with the softer side of IoT devices, an important aspect is to get access to this firmware, especially if it can't be extracted from the device. While one possibility is to search for such firmwares online, another possibility we investigate is to listen to the device during execution to extract further information. Tobias is working on this.
Here are aims to recover the source code of a given device solely from its electromagnetic emanation. Was that even possible? You see, the power consumption of a device depends on the program it is executing. For the switching of transistors, current is constantly changing, producing an electromagnetic field. Now we can measure this electromagnetic field with a so-called need-free probe. Due to complex pipelines or jittering effects and modern processes, we need a little more sophisticated approaches. Therefore, we borrow ideas from cryptography and even image recognition to implement an actually usable side-channel-based disassembler.
Once we have the firmware, we need to analyze it, which is Michael's field of work.
My field of expertise is binary analysis and reverse engineering. and in my spare time, I'm helping out Georg with managing the CTF team. While analysis tools for other processor families like ARM are decent, they are basically non-existent for AVR, which is why I've developed a full system emulator with the specific purpose of firmware analysis in mind. Using this emulator, in combination with a fuzzer, we can analyze firmware binaries for vulnerabilities, or for example, audit libraries for the popular Arduino project.
While currently emulation takes some manual effort to properly consider peripherals, Christian, who would currently be in New York, is working with Sebastian on automated emulation of IoT devices.
To do so, we designed a modular architecture and we are currently implementing a first prototype. Let me give you an overview of the architecture. The crawler constantly monitors the internet for new firmware samples and stores new identified firmware URLs into a database. After the discovery, the crawler notifies the task scheduler that a new firmware sample can be downloaded. In general, the task scheduler coordinates the tasks for all components. This allows the parallelization of tasks, and since all components are deployed in containers, we are able to scale the system to our needs. The downloader component stores the firmware samples to a file server. In the next step, the classifier component is triggered, and this component classifies the firmware samples and extracts as much information as possible. As you can see, the classifier contains different plugins. For example, the static processor analyzer uses pre-gained knowledge to determine the processor family and peripherals. After the classification, the framework creates suitable virtualization instances. A distinction is made between firmwares which contain Linux operating systems and firmwares which are executed on bare metal processors. The first use case is firmware fuzzing and symbolic execution. This will allow us to dynamically probe IoT firmware for security issues. Another use case are IoT honeypots. Due to the framework, we are able to collect IoT-relevant malicious empirical data, we can formulate IoT-centric attack signatures, and we can generate IoT-specific technical threat intelligence.
Now, if we can analyze devices, the next step is to search for vulnerabilities and possibly harden the firmware against further attacks. This is the domain of Matthias.
My work is currently centered around embedded systems security, with a focus on devices that are too constrained to operate a regular operating system like Linux or Windows IoT Core. Due to the software and hardware heterogeneity of these systems, state-of-the-art security features are seldom available. Therefore, my work focuses on techniques to implant security features into embedded firmware at the post-compilation and linkage level in such a way that the system's constraints are still obeyed and as many of the detected potential vulnerable spots are protected.
So, we have all these different IoT devices that have to come from somewhere, and nowadays these factories are also connected to the internet to enable remote supervision. But of course, this also exposes the factories to the risk of attacks, a topic that Laura, our Femtech intern, and Matthias are investigating.
In my research, I focus on automating security risk assessments in the industrial domain. In my latest work, I developed a method for automating the security risk identification step according to the IEC 62443 series of standards. This method can be seamlessly integrated into the engineering process, since the engineering artifacts are directly used as an input. For example, engineers create AutomationML artifacts, which include the plant topology and system configuration data. This data is then transformed to ontological knowledge and enriched with additional know-how, such as vulnerability information. The method will then yield automatically the vulnerabilities of the plant components and the corresponding attack consequences. Finally, all this information can be represented and visualized as an attack graph in order to illustrate the most critical attack paths.
With this, we conclude our tour through the IoT Systems and Industrial Security Group. Thank you for watching, and we hope you enjoyed the show.